Hello, everyone. First of all, I would like to thank everyone for participating in this conference, and thank you for having me. My name is Eritrea, and I'm from Addis Ababa University. And I did my research under African Center of Excellence for Water Management, and the title for my research was Effectiveness of UV Disinfection against Cercaria at Selected Wavelengths using UVC LEDs for Schistosomiasis control. When we come to the introduction part, schistosomiasis, also known by its generic term Bilharzia, is a parasitic infection that is caused by flatworm of the genus Schistosoma, and it can cause acute and chronic disease, and it's been a growing public health concern in many parts of the world, and it is estimated to be endemic in more than 74 countries, of which 46 are found in Africa, which indicates that this disease is much more intense in Africa, and it's also considered to be endemic across Ethiopia, both in rural and urban settings, and it's estimated 55.9 million people live in schistosomiasis endemic area in Ethiopia. And this map shows the distribution of schistosomiasis throughout the world and the distribution of schistosomiasis in Ethiopia. So since it's been a great public health concern, different disinfection methods were used to control this disease, including snail control, chemotherapy, chlorination, and also UV radiation. And our research focused on UV radiation since few studies have been done on the effectiveness of UV light in inactivating schistosomiasis, or the parasite that causes schistosomiasis, which is called Cercaria, when compared to bacterial and other pathogens. We also focused on UV radiation since it's been becoming a popular disinfection method due to its great benefits than the conventional methods. And we thought that more information was needed to fill in the gap on the effectiveness of killing the parasite that causes schistosomiasis and controlling the disease. So we used a new UV technology, UV radiation technology, that is UVC LEDs, which is relatively new disinfection technology that's considered to be both environmentally friendly and effective. And when we checked methods, there was no detailed method in standard measurement protocol for determining the UV dose needed to activate Cercaria, which is the parasite causes schistosomiasis disease. So we want to fill in this gap by providing the information on how effective this instrument is in inactivating Cercaria. So holding this in our mind, we came up with a main objective and specific objective. Our main objective was to examine the effectiveness of UV disinfection against Cercaria for schistosomiasis control at selected wavelengths using UVC LEDs. Our specific objectives were two, and that is to compute the UV fluence, which is the product of average fluence rate and exposure time that is required to inactivate schistosome Cercaria. Our second specific objective was to examine the effectiveness of UV disinfection against schistosome Cercaria at 3 selected wavelengths using UVC LED, and we also wanted to check what wavelengths is effective and what exposure time was needed to inactivate schistosome Cercaria using UVC LEDs. To the methodology, the first thing was to select a sampling site. So we chose a sampling site that is known to be endemic for this disease. So we chose Lake Zuwai and Tekruha. Both are located the central and southern part of Ethiopia, as you can see on the image. And the second, or the next thing, was sample collection. So we collected live snails. This is because snails are known to be endemic host for this parasite, that is Cercaria. So we collected live snails randomly from the bank of Lake Zuwai and Tekruha, as you can see from the first picture. And then the collected snails, as you can see on the second image, were put on water in some aquatic microphytes. This is to mimic the natural environment for the snails while transporting. Then the second preparation was the next step. So shading snails were placed in a small bottle containing 1 up to 2 ml of bottled water, as you can see on the first image. Then the snails were left to shade under direct light for about 15 minutes, as you can see on the second image. Then after the snails released the Cercaria, 100 up to 120 Cercaria were prepared into 100 microliter, as you can see on the last image. Then, the next thing we did was measuring the radiance and calculating the exposure time. So this is done based on the standardized protocol by Bolton. So the first thing that we did was we measured the central radiance. Then we added or we multiplied different factors to the central irradiance. Those are petri dish factor, water factor, divergent factor, and reflection factor. So once we get all these factors, we multiplied it to the central irradiance to get the average fluence. Once we get the average fluence, 1 over the average fluence is the exposure time needed for 1 UV dose or 1 millijoules per centimeter square. Then after we gain the radiance and the exposure time needed, the exposure procedure was done. And this is done by putting a stir bar in a sample containing 3.8 ml of solution. And we expose them to the UVC LEDs at three wavelengths. This is 255 nanometer, 265 nanometer, and 285 nanometer. So we exposed our sample for the calculated fluence and exposure time. Then after exposure, after exposing the samples to UV light, the Cercaria was counted using a microscope, as you can see on the second image. Then the total number of Cercaria was counted by adding 20 microliter of Luglos. This is to fix and stain all the Cercarias, as you can see on the last. Then after finishing all the experimental procedure, we analyzed our data. So the experiment was done in triplicate, and we took the average, then percent of alive Cercaria of the sample and mean percent of alive Cercaria of the control was calculated. And using the above information, the log reduction was calculated. And we also tried to see the correlation between the fluence and log reduction. So when we come to the result in discussion part, we computed the fluence and the exposure time for each 3 wavelengths. So we found out the average radiance for each wavelength to be 0.260 milliwatt per centimeter square for 255 nanometer, 0.297 milliwatt per centimeter square for 265 nanometer, and 0.694 for the last wavelength, which is 285 nanometers. So based on the principle proposed by Bolton, 1 over the average radiance is the exposure time needed for 1 millijoules per centimeter square. So we calculated for each wavelength using this principle, and using the same principle, we calculated the exposure time for all the 10 UV dose that we used in our experiment, as you can see on the table. So after calculating the exposure time, so we exposed the Cercarias to this UV light. So this picture shows, the first picture shows that the Cercaria movement at 0 millijoules per centimeter square. So as you can see, the tail part is contracting and relaxing, which shows a movement within the sample. So that means the Cercaria is alive and have the tendency to affect. And the second image shows the contraction was, the relaxation was decreasing. As you can see, the tail has a shape of fork, which shows the tail is weakened, and the movement was also weakened, but the Cercaria was still alive. And the third image shows the Cercaria detached from the body, the head and the tail part. It's detached from the whole body at 300 millijoules per centimeter square. So when we see the fluence versus log reduction for each wavelength, is when we come to the first wavelength, that is 255 nanometer. They were active Cercarias until the last dose or fluence. There were more than 30% of alive Cercaria when the exposure was done, and less than 1 log reduction was achieved, which is 0.5 till the last fluence. And when we come to the second UV wavelengths, that is 265, it was more effective than the first wavelengths, and a 1.5 log reduction was achieved at the exposure time of 16 minutes. And more than 40% of Cercaria were alive in the fluence 1 to 200 millijoules per centimeter square. But number of alive Cercaria drastically decreased at the last fluence, which is 300 millijoules per centimeter square, achieving 1.5 log reduction, which is 90% inactivation. And when we come to the last wavelength, that is 285 nanometer, it acted more efficient than the other 2 wavelengths. At 200 millijoules per centimeter square, we found 1.1 log reduction, that is 90% inactivation. And at 300 millijoules per centimeter square, we found 2.1 log reduction, showing 99% inactivation, which shows that almost all Cercaria were dead at this UV dose or fluence. We try to see the correlation between the fluence and log reduction. So as expected, the correlation has a strongly positive correlation. That means when the fluence was increasing, the log reduction was also increasing. So when we come to the conclusion and recommendation part, we found out that 99% of Schistosome Cercaria can be disinfected at wavelengths of 285 nanometers using 300 millijoules per centimeter square using UVC LEDs. So we concluded that this instrument, this new UV technology, is capable of disinfecting the parasite Cercaria that causes schistosomiasis, but it needs further study in order to enhance and decrease the UV dose. And we also recommend more studies in meteorologists. Meteorologists should be investigated when it comes to the mechanism of DNA and RNA damage. And we also recommend that water should be pre-treated before using this machine. And also we will recommend to use this disinfection instrument or UVC LEDs coupled with other disinfection methods to gain a better result. And we also recommended that public awareness should be out there in the endemic area to also decrease the disease in the future. And finally, I would like to acknowledge my advisors, Halaka Zoga, which is an associate professor in Addis Ababa University, Lucinda Hazel, and Professor Hamilton, both from Imperial College of UK. And my biggest gratitude to African Center of Excellence for Water Management and Wiser Project for supporting this research study. These are some of the references that I used.